Hi, welcome back. In this lecture, I'm going to discuss benchmarks and what are the most important benchmarks in HPC. So first of all, what are benchmarks and how are supercomputers measured? Well, the first question we have is why do we want to measure or rank a supercomputer? And what is the purpose of an extreme scale system? So if the purpose is to do science, is to enabling science on a large scale, that there should be a measurement in place to be able to compare different supercomputers. Also, there is a big value in having a way to compare different supercomputers before either making a purchase or making a request for an allocation. In particular, in this case, the question will be, will this system be able to solve my problem? Will be the right system to solve my problem? And second, is the system the right size? Right? Is too big for the small application I want to do, or is too small for the large scale simulation that I want to complete? So what are benchmarks? Benchmarks are methods used to provide measurements that allow similar things to be compared. So it's a measurement with the goal of comparing things. High performance computing benchmarks are typically one or more program that must be run correctly. So you always need to check that the solution is correct with a predefined input. The measurement, the output of this benchmark is usually either a time, execution time, or a rate. Like for instance, we already seen floating point operation per second. These slides present some popular benchmarks that we're going through in the next slides. The most famous benchmark in HPC is called HPC LIMPAC, and is in short HPL. It is benchmark that is used for ranking the supercomputer, the most powerful supercomputer in the world. This rank is called top 500 because it includes the first 500 most powerful supercomputer in the world. So what does this HPL or HP LIMPAC does? Well, in summary, it solves a linear system. It solves a system of n linear equation using a quite old method, Gaussian elimination. In this particular case, the matrix is dense. This means that the number of non-zero is low. The complexity of the execution time scales roughly like 2 multiplied by n cubed divided by 3. And these are roughly an estimate of the floating point operation only, without taking care of the memory. The memory is roughly n square, right? So there is, if we divided the floating point operation by the memory data movement, we will have n cubed divided by n square, right? So it's highly dominated by floating point operation. The results of HPL on different system is updated twice per year in connection to two major supercomputing conferences. First in November, supercomputing, and that is typically a conference in US, and then second in June at the ISC, that is a supercomputing conference that is held in Europe. So why this is one of the most famous HPC benchmark? The reason is that solving a system of linear equation is at the heart of many computational science problems. Right? So when we discretize a continuous equation on a grid, we come up with a PDE that is corresponding to solve a linear system on the grid. So what is the major issues that people start complaining about HPL? Well, the major issue is about that almost all the large linear systems are sparse and are not solved with the Gaussian elimination. So just think about, when you discretize a Poisson problem, for instance, you do in the 3D, the structure of this matrix is going to be basically a pentadiagonal. This means that it's going to have 5 diagonals, and the rest is going to be all 0. As you can imagine, such a matrix is largely sparse, so this means the number of zeros in the matrix is very large. So typically, all these linear systems coming from Poisson equation discretization or Navier-Stokes equation are very sparse. So the number of zero in the matrix is very high. And also, there have been major development in the field of numerical analysis. So people don't use anymore Gaussian elimination, but more advanced methods like Krylov methods. So people are trying to move forward from Lynchmark. Is still the main benchmark to compare the performance of the different computer, but we are also looking at something that is more representative of HPC workloads. An example is HPCG. HPCG stands for High Performance Conjugate Gradient, so it solves a conjugate gradient linear solver that is much more advanced than Gaussian elimination. And HPCG is designed to exercise computational and data access patterns that more closely match a different and broad set of important applications using sparse matrices. It completes many different operations. The most important one and the most representative of HPC workloads are sparse matrix vector multiplication, vector updates, so just scaling vectors, global dot products, so calculation of inner products, local symmetric Gauss-Seidel smoother, sparse triangular solver, and the multi-grid preconditional conjugate gradient algorithm. So let's move to Stream. Stream is extremely important benchmark that is used to measure sustainable memory bandwidth. We will use more and more Stream benchmark in the course starting from the next lecture. So what it does, it basically measure how the data transfer are fast, and it measures sustainable memory bandwidth. It comprises 2-4 operation or kernels. So that means that we can measure the performance of a 4 operation. We can measure how fast our system is able to copy one array to another array. How fast is to make a scaling operation, to do an adding operation, and then what is called a triad. That is basically taking a vector and adding another vector and summing up with another vector that is being scaled by the factor of a. So it's basically, most of these are very simple kernel. They're very close to actually copying one array to the other one, so as a small variation of one over the other one. But there are 4, and we will measure the performance of these 4 kernels. So how big is the array that we are trying to copy, scale, adding, or using tried kernel? They're typically very large. So the X, Y, and Z are large, and we will explain what very large means later in the course. You might already imagine that is related to the fact of different memory that are present in the supercomputer. Another collection of benchmark that has been quite famous now is not used as much as in the past is called HPC Challenge, and it's an attempt to broaden up the HPC Lynchmark benchmark to a suite of benchmarks. So it's a collection of different benchmarks. It does include the HPC Lynchmark, but also included the DGAM, that is the dense matrix multiplied. In this case, D stands for double, not for dense. So there is DGAM and SGAM. So D is for double precision, S is for single precision. It includes also the stream to measure the performance of the memory and the data movement on our system. Is also include a quite important operation in HPC, that is the transposition of a matrix. So there is one particular benchmark called ptrans that is looking at measuring how fast we are in transposing a matrix. We will look at the transpose operation later on in this course and try to make a performance model. It also includes a random access benchmark. They basically pick it up randomly, one cell, one element in array, and accumulates a value. And also include one of the most famous kernel in HPC, that is the fast Fourier transform. In particular, in this case, it completes 1D fast Fourier transform, and also have some benchmark to measure the performance of the network, in this case called BF, that is looking at the bandwidth and latency of the network of the supercomputer. So one of the problems of this collection is that the characteristics are not distinct, in the sense that HPL is already completing many DGAM operation. So a DGAM is actually a part of the HPL benchmark. And as I told you before, it used to be used quite a lot in the past, but is less used today. One arising an important benchmark is the Graph 500, and is an attempt to provide an alternative to HPL for graph problems. So HPL is for measuring the performance of a traditional HPC application, a linear system. The Graph 500 aims at solving graph problems. So the results are available since November 2010. So we have less historical data when it comes to the performance of supercomputing solving graph problems with respect to HPL. That goes back to 20-30 years back in the past. So what the Graph 500 does, well, is solving the BFS problem, the breadth first search. And it provides, if you go to the website of the Graph 500, it provides reference implementation for OpenMP and NPI, so we can run it on supercomputer right away. However, the benchmark allow us to use the algorithm that is best fit to the system. So from the description from the benchmark, they do not constrain the choice of BFS algorithm itself. As long as it produces a correct BFS tree as an output, the benchmark itself is good, right? So this allows different people to try to adapt the algorithm to the machine to achieve a higher performance. So the major performance metrics is a rate, so it's not execution time. Performance metrics are also called the figures of merit, FOM. So in this particular case, it's called taps. That is the number of edges that are being traversed per second in the graph. A very famous collection of benchmark is the NAS parallel benchmark. This is derived from applications that are important to NASA. So in particular, all computational fluid dynamics application. The original version described problems to solve, but left implementation to the user. It was defined before there was a standard for programming and for programming parallel system. So it was designed before actually MPI and OpenMP. Today, Today, NASA provided standard implementation both in MPI and MPI plus OpenMP, but many different versions are actually available. So what this benchmark collection includes a sorting of an integer. It includes the conjugate gradient we saw also in the HPCG. It also includes a multigrade that is also included in the HPCG. The solution of a PDE using 3D FFT. So we have our problem, we go to spectral space using FFT, and then we solve the problem in the spectral space, and we go back to real space using 3D FFT. So it's much more than just solving the 3D FFT. It's actually an application using 3D FFT. Together with these kernels, we also have 3 pseudo CFD applications that are mimicking large CFD, computational fluid dynamics application. See, this is one of our favorite benchmark collection that we have been using for our papers in benchmark system, but also trying to new different things. So in particular here in the bottom of the slides, you see a paper where we use the NAS parallel benchmark and PB to estimate the performance and accuracy of a POSIT that is an emerging floating point format. So what people are using today? Well, people today are looking at a collection of different benchmarks. But the benchmark in this case are not just a very simple operation, very simple kernel, but instead they try to be code that are mimicking larger application. These are typically called mini apps. So one of the first most important is the Coral collection. Used for the most recent big DOE procurement. DOE is the American Department of Energy that is responsible to buy a large supercomputer. So actually, before buying supercomputer, we have the DOE set a number of different requirements when it comes to the performance of different benchmarks. So one of the benchmarks that provides to the vendors, to the people selling the supercomputer, is the Coral benchmarks, right? So a set of application, when the vendor needs to use this benchmark, possibly optimize and provide back what are the performance measurement to the OE before buying the supercomputer. So it's a large set of different benchmarks, ranging from almost full-fledged application to micro benchmark that are basically looking at just measuring data movement or some latency and bandwidth of the network. A second very important benchmark suite is the ECP exascale proxy application. So these are they're more like small application. They're called also mini apps. They are small simplified codes that allow application developer to share important features of a very large application. So pretty much all the large application, they provide a large application, but also they provide a smaller application that can be given to the computer science. So this is typically smaller in size, is easier to set it up and run without knowing any specific internals of the large application. An example here is, for instance, the neckbone mini application is that is mini application related to the NEC 5000, that is a large scale computational fluid dynamics, largely used at KTH. So let's look at rank using benchmarks to rank system. So this is the top number 5 in the top 500 list in November 2019. As I told you, this list is updated twice, one in November with the supercomputer, one in June with the ISC. So here you have the first 5. We know already Summit and Sarah from the second lecture. We also look at the third one. We have in third and fourth position, we have 2 Chinese machine with a Chinese processor. And the second, while Tianhe 2 also has some Intel. So this was due before US had an embargo on American chip to China. So China is developing its own processor and accelerator for HPC. In the fifth position, there's a Frontera that is Intel Xeon. So if you look at developed by Dell, so if you look at what is the architecture, you see mostly these are processor with accelerators. So is what is the performance of the HPL is this Rmax here that is in teraflops per second, right? So, and this is the number that we get from running the HPL on that particular system. And that particularly on the right, next to the Rmax, that is the performance given by HPL, we had the Rpeak, that is the theoretical peak that can be achieved from the system. On the last column, we also have the power. So if you compare the values of Rmax divided by Rpeak, this is going to be a fraction. I give you an idea of the efficiency of the system. So you can see that most of the system the efficiency, even though the HPL is quite optimized, the efficiency is rather low, in the range of 60-70% in most of the cases. Let's use now a different benchmark to rank the current system. We saw that the HPCG is a more representative case of HPC application because it has sparse matrices and that are more common in HPC. So it's no surprise number one and number two are still the same one. So DOE did a good job in that two machine. There's a little bit difference in the number 3, 4, and 5th in this application. So we have Trinity in Los Alamos, we have a machine from Japan, and then we have in the 5th position we have a Peace Diane, that is the fastest European supercomputer in Switzerland and in Europe. So let's so the two columns here present Rmax, that, as I told you, is the number we got from a HPL. And next to it, we have the results from the HPCG. So one thing is we should notice that the performance of the HPCG is much lower than the performance by HPL, right? So real-world HPC applications do not perform as well as HPL. Let's look finally to the results from the Graph 800. That is the benchmark that is looking at more at data-intensive graph-based application by solving basically a BFS. So in this case, the figure of merits is the tabs. So these are transverse edge per seconds. This is quite surprising list. So there is Summit is not anymore number one. So it's not it's very good for HPC, but for graph problem is not as good as other machines. So here is in the 4th position. And number one, well, in the first 3 positions, actually quite old machine, basically 2015 and 12. So number one is Sunway Taiyu Light in China. We have the Sequoia system in Livermore, and then we have the laboratory. We have a Mira that has been decommissioned in these years in Argonne National Labs. And the 5th position we have SuperMOOC, that is a German system in Garching. So we've seen a number of different benchmarks. So where are HPC system going? So there's been a lot of discussion on look at benchmarks. We saw that to have a good benchmark is very good, especially if you guys are buying supercomputers. So you want to have a benchmark that are representative of the application that you're going to run on your system. So top 500, the HPL is the most used benchmark used, followed by the HPCG. Stream, random access, and GAF 100 are also common. So it's quite common that during the procurement the performance of these different benchmarks are asked. In this course, we will use Stream a lot for performance modeling to get an idea how our memory system is performing. There is an increased interest in the community in more application-oriented benchmarks. For instance, proxy or mini application, they are mimicking larger application. So we look at a different rank of supercomputer, the top 500, the HPCG, and the GAI 500. And we saw that most of the machines are at least in the top 500 and HPCG, they're using GPU for HPC. So the reason for that GPU and accelerator in general have a very nice ratio of the power per the number of floating point operation for power that need to do this operation. So in order to meet the requirements that are coming from both from performance, high number of floating point operation, and power, we want to have the lower power possible in the system. So to meet these two requirements on power and performance require a specialization in hardware. So to look at hardware that has very good efficiency when it comes to power usage for computing. So this was the slides. I gave you an overview of the different HPC benchmark. In the next lecture, we're going to look at again performance modeling, but in this case sparse matrix vector multiply, that is more representative kernel of HPC application. Talk to you soon.